I'm going to give you a related rates example, kind of the first word questions you see with related rates, and it's ripples in a pond. It's a classic question, okay? I don't care what calc book you're looking in, you're going to find this one somewhere. And basically it goes like this. I'm not going to write the whole thing down. Is you drop a pebble in a calm pond. It just sounds so serene and lovely. And so you drop it, boom, there's your impact. And from that, it ripples out. And those ripples are circles. Sort of, right? And so what's happening is this circle is expanding and expanding and expanding. And so there are things that are happening. So we have when this expands, you have a change in your radius and a change in your area. And so those are the two rates that are going to be related to each other. So they'll give you an instance. So they'll describe the whole situation, and then they'll say, hey, when, and they're going to have to give you a rate, and they're going to have to give you an instance. Okay, very likely a radius here. So when r equals 6 centimeters, find the change in area over the change in time. And then they'll also have to give you, in that question, you'll notice they'll give you the change in radius is something like 2 centimeters per second. Okay. So once again, calm pond, it's dropped. They notice that the rate of the radius is expanding at 2 centimeters every second. That's a constant rate. That's nice. But your area is going to change as well. So at this particular instance, let's see what's going to happen. So we know our area formulas for a circle. So you have to know your area formula for a circle. We're going to take the derivative with respect to time. That happens almost exclusively in related rates. Like every related rates question is taking the derivative with respect to time. So this is going to turn into the derivative of A, so the derivative of area there with respect to the time. Here, remember pi is just a constant, so we're going to bring the 2 out front of the pi. R, so just power rule, times dr over dt, okay? So those implicit differentiation ideas are popping up now. And we're going to plug in what we know. Well, we know an instance when the radius is 6. We know an instance that dr over dt is always 2. So that's what we got. And so the change in area with respect to time is 2 times 6, which is 12, 12 times 2, which is 24 pi centimeters squared per second. Okay, it's a rate. Okay, make sure you have a time in there. And obviously, since it's an area, you need to have square units. And realize that like all you have to do on a question like this is change one little thing. So I could say, hey, when the radius is 5, find the change in area with respect to time. You're like, oh, okay. So we'll keep this guy constant. So try it again, folks. Pi r squared. The derivative would still be the same, right? So you're going to take that derivative first. We're not going to try to simplify anything crazy here. We're going to take that derivative of the area equation, and then we just plug in what we know. So now this is 5 centimeters. And this is 2 centimeters a second. So not much change. So what you notice though is you drop a pebble, circle's expanding, the radius constantly growing 2 centimeters a second. Every second 2 centimeters, every second 2 centimeters. But notice what's happening. When the radius is 5 centimeters, this is how fast it's growing. When the radius is 6 centimeters, this is how fast it's growing. So the one rate will consistently change. Okay? Hopefully this helps. A lot more examples to come.